Hallo, it's dumplet here. Here's an item on number theory. M and n are positive integers such that m factorial plus 5 is equal to n cubed. Now we're asked to solve all possible ordered pairs mn. Credits to the Art of Problem Solving community for this item. As usual, pause this video if you'd like to give this item a try. But if you're done, let us dive into the solution. Now first things first, we're going to observe the given equation. So m factorial plus 5 is n cubed. Now this is a very common situation where it involves two things, a power of a positive integer, n cubed in this case, the third power, and then the other part is a factorial. So in this case, m factorial. Now the typical thing to do in these examples is that, well, because you can try to observe this equation under a mod, let's just say a random positive integer, let's just say k. Because, well, if as m grows big enough, it's going to be 0 modulo k, and we might try to see the possible residues of n cubed modulo k. Now, choosing k is very essential to this question because, well, we want to choose k that's actually going to help us and kind of simplify the question a bit. And I am going to tell you that we are going to use mod 7. Now you can try to memorize that, okay, whenever you have a cube, we're going to do mod 7. Now if I were to alter this question a little bit, instead of n cubed, let's just say I have n squared over here. Now the n squared, it actually motivates us to do either mod 3 or mod 4, but these numbers don't really just come out of nowhere. There is a very nice reasoning behind why we select, in this case, for the n cube, we're going to have mod 7. Now the reason being is because of for example, we know that by the Fermat's little theorem, we know that a raised to n, I should use n raised to 6, it's going to leave a remainder of 1 if I divide it by 7. Now obviously that's the case where n is not divisible by 7, so if n was divisible by 7, then there's going to be the possibility of a 1. Now why do we use 7? It's because, well, the exponent here is 6, because, well, phi of 7, so Euler's totient function, phi of 7 is 6, and 3 is half of 6. So, well, apparently we just have to take the square root here. So if I take the square root, I'll get that n cubed is equal to, well, if n to the 6 was 0 mod 7, then n cubed would be 0 mod 7 as well. And if n to the 6 was 1 mod 7, that's going to give two possible square roots, 1 and negative 1, under mod 7. Now with this, actually, we can try to observe under mod 7. Now that we have this identity, that this property, that n cubed, it's going to leave either one of these three. Now why is this helpful? It's because if we try to observe mod 7, we get that m factorial, let's try to make it equal to n cubed minus 5 first, so subtract 5 on both sides, and we know that n cubed minus 5 is going to be congruent to, well, if n cubed was 0, it's going to be negative 5 mod 7, which is just 2 anyways. If n cubed was 1, well, 1 minus 5 is negative 4, that's the same as 3. And if n cubed was negative 1, n cubed minus 5 would be negative 6, so 1. And what's important here is that, well, 2, 3, and 1, they're not 0, so m factorial is not divisible by 7. Now with this, we can already conclude that, okay, so if m was greater than or equal to 7, then obviously m factorial would be congruent to 0 under mod 7. But we know it's not possible to have a solution because n cubed minus 5, whatever the value of n is, it's only going to be 2, 3, or 1 modulo 7. So that is the reason why it is very nice for us to kind of choose a value of, well, in this case, the value of 7, and take mod 7 on both sides to kind of restrict the value of m. So m greater or equal to 7 leads to a contradiction under modulo 7, so we ignore that. So we have to consider values of m less than 7. And that is the reason why, essentially, we just have to consider values of m less than or equal to 6. Now it's just finitely many cases to check, and we just have to substitute m equals 1, 2, 3, 4, 5, and 6, and to check for n. Alright, let's do it one by one. If m is equal to 1, then m factorial plus 5, that's going to be equal to 6. So 6 equals n cubed, no possible solution, since the cube root of 6 is not an integer. So we ignore that. Next, m equals 2. 2 factorial is 2, so 2 factorial plus 5 is 7. Again, 7 equals n cubed. 7 is not a perfect cube, so no solution here. If m is equal to 3, m factorial is 6. So 3 factorial plus 5 is 11. 11 equals n cubed. Well, 11 is not a perfect cube, so no solution here. If m equals 4, m factorial becomes 24. 4 factorial plus 5 is 29. 29 equals n cubed. Still no solution because 29 is not a perfect cube. We try m equals 5. m factorial is 5 factorial, so that's 120. So 125 is equal to n cubed. And here we have the first solution. 125 is 5 cubed, so we're going to get from here that n equals 5. So we have one possible solution thus far. M equals 5 and n equals 5. We have one more case to check. M is equal to 6. So 6 factorial, that's 720. So 6 factorial plus 5 is 725. That's equal to n cubed, but 725 is not a perfect cube, so m equals 6 doesn't work. And there we have it. We've exhausted all possible cases that we have to check. So values of m less than 6. After checking everything, we realized that it's only m equals 5. So that's going to give us n equals 5, and therefore the only possible solution, or the only possible ordered pair, mn, is 5, 5. And this will be our final answer. Hopefully you guys learned something new from this video, and I'll see you in the next one. Bye bye!